So imagine trying to hold a perfect uninterrupted Wi-Fi signal, right? But you're standing on a rocking seesaw.
Oh, wow. Okay. Sounds fun.
Yeah, but wait. You're also surrounded by a corrosive salt tornado, and you're right next to a giant spinning microwave.
Right, yeah, that paints a picture.
And on top of all that, your antenna has to keep this, like, millimeter-perfect lock on a satellite. A satellite that's about the size of a dining table, moving at 17,000 miles an hour in low Earth orbit.
Yeah.
And if you drop even one packet of data, just one, your video call completely fails.
Yeah. I mean, honestly, that is the daily, grueling reality of maritime connectivity. It's wild.
It really is.
We constantly talk about modern hardware as if it exists in a vacuum, you know? Like, you plug a sleek box into your living room wall and it just works.
Exactly, yeah. Plug and play.
Right. But the moment you take that kind of high-performance electronics offshore, the environment is actively trying to destroy it. I mean, physics always gets a vote, right? And on the water, physics is just ruthless.
Which is exactly our mission for you today. We are taking a deep dive into the underlying engineering of bringing, true enterprise-grade, high-speed internet to the open ocean.
It's a fascinating topic.
It really is.
Yeah.
So if you want to understand how environmental constraints completely dictate technology deployment, and like how engineers actually solve those physical bottlenecks, you are definitely in the right place.
Absolutely.
We are parsing through a really comprehensive technical guide. It was published in May 2026 by Michael Rabilio. He's the founder of Concord Marine Electronics.
Out in Fort Lauderdale, right?
Yes, exactly. And the guide is titled, What are the Hardware Requirements for Starlink Marine?
And what makes this source material so compelling to me is that it just completely dismantles the idea of Starlink as this consumer plug-and-play gadget.
Yeah, the illusion of easy tech.
Right. It really forces us to look at satellite internet as a singular node in a highly complex, totally ruggedized system.
Yeah.
You cannot just throw raw processing power at a marine environment and expect it to survive. It just doesn't work.
And I think that's the core disconnect here. People treat maritime deployments like they're just outfitting a stationary office building downtown.
Exactly.
But reading through the environmental baselines in this guide, it becomes pretty obvious that a boat is essentially like a localized earthquake zone that's just wrapped in a saltwater bath. Kind of reminds me of taking an indoor house cat on a roller coaster.
That's incredibly accurate. The mechanical stress alone is just staggering. I mean, you have these massive diesel engines, right?
Right.
And they're generating these low-frequency harmonic vibrations that will literally, and I mean literally, vibrate solder joints apart if the equipment isn't properly isolated.
Oh, wow. So it physically shakes the internal circuits to pieces.
Exactly. And then you add the constant, violent multi-axis movement on top of that. You've got pitch, roll, yaw, and sometimes all three at the exact same time.
And that structural movement fundamentally changes the math for the antenna, doesn't it? Because, the phased array inside that Starlink dish, it uses electronic beamforming to track those low Earth orbit satellites.
Right. It's steering the beam electronically, not physically moving.
Right. So if the boat is plunging into like a 10-foot wave trough while traveling at 20 knots, the dish has to instantaneously calculate and adjust its transmission angles.
It's constantly compensating.
Yeah, to compensate for the vessel's movement, all while still tracking the satellite's orbital trajectory across the sky.
It is a massive computational load. Huge. And, that's before we even talk about the digital traffic load from the users.
Right, because it's not just one guy checking his email.
Not at all. The guide highlights that a modern yacht's internet system, a single connection, has to seamlessly handle, well, a lot. You've got the owner's communications, guests streaming 4K video, all the crew's personal devices.
Don't forget the onboard audio-video distribution systems.
Yes. And crucially, the vessel's remote engine monitoring and telemetry tools. All of this is fighting for bandwidth at the exact same time.
So treating the dish simply as this magical antenna rather than, the heavily burdened tip of an entire network spear is really where most deployments fail.
Precisely. It's a whole system.
So knowing how hostile this environment is, let's look at the actual hardware arsenal. The guide outlines the standard Starlink kits, the Standard 4 and Standard 4X. And it does note they are technically approved for boat use.
Technically.
But it heavily, heavily pushes the Performance and Performance Gen 2 kits as the mandatory baseline for serious marine applications. And, I have to push back on this just a bit.
Okay, let's hear it.
Because I see people throwing the standard, cheaper dish on their little center consoles all the time, and it seems to work fine. So is the performance kit strictly necessary, or is it, just an upsell for the wealthy yachting crowd?
I get why you'd think that, but it is absolutely not an upsell. It is an operational necessity for sustained offshore use.
Really? Even with the price difference?
Yes, the source data is very clear on the threshold limits of the standard hardware. Like you said, yeah, a standard dish is fine for a small center console. If you're just heading out to a sandbar for the afternoon, the demand is low, the exposure is temporary, it's fine.
Right, you're not crossing an ocean.
Exactly.
Yeah.
But the standard hardware, it relies on thermal profiles and weather sealing that simply aren't rated for permanent, unprotected exposure to extreme marine elements.
So you're talking about the physical casing of the dish itself here.
The casing, the internal thermal management, the field of view, all of it. The performance kits are specifically engineered for permanent installation and for mobility while underway.
Right. They have to survive a lot more.
Yeah, they're literally armored to withstand extreme cold, high heat, driving sleet, heavy rain, and high wind shear. And they do all that without thermal throttling or physical degradation.
And from a throughput perspective, the performance hardware is required to reliably hit that 400 plus megabits per second download speed the guide talks about, right?
Yes, especially under heavy multi-user loads.
Because if you have guests on board who expect uninterrupted video streaming while the vessel is, crushing through waves offshore, a lighter duty standard setup is going to bottleneck.
It will absolutely choke.
It's far more sensitive to structural obstruction and weather attenuation, from what I understand.
Precisely. If the operational expectation is long-term reliability and heavy concurrent network traffic, the performance hardware is literally the only viable starting point. You have to match the tool to the severity of the environment.
Okay, that makes sense. So let's assume you've made that investment. You have the performance hardware in hand. The next phase, actually mounting it to the vessel, seems to be this structural and electromagnetic minefield. Like, location is everything.
Oh, it is the single biggest point of failure in physical deployment, without a doubt.
Wow.
The guide details the optimal structural targets, right? So we're talking the hardtop, the radar arch, maybe a mast platform, the flybridge structure, or a stabilized electronics platform.
You just want to get it as high as possible.
Basically, yes. The objective is maximum elevation with an unobstructed 360-degree view of the sky.
But it's the hazards you have to dodge that I find really fascinating. The guide explicitly warns against placing the dish in high heat exhaust zones. Which, I understand the baseline heat issue. You obviously don't want delicate electronics baking in 400-degree diesel exhaust.
Right, that's just bad practice.
But diesel exhaust is also incredibly oily and dense. So does the physical soot buildup on the face of the dish actually impact the RF transmission?
Oh, it absolutely does. Diesel soot has conductive and dielectric properties.
Really?
Yeah. So if you allow this thick layer of carbon and oily residue to just bake onto the radome of the antenna over time, it can significantly attenuate the radio frequency signals. It totally degrades your connection. You are physically blinding the array.
That is wild. But I guess an even faster way to blind the system is mounting it in what the guide calls a radar shadow.
Yes, and this happens a lot.
This goes back to my spinning microwave analogy from the intro. Yachts utilize these massive open-array radars, right? They sweep the horizon with high-frequency radio waves to detect other ships and weather patterns.
Right, and those radar arrays, they emit intense bursts of electromagnetic energy.
Like seriously high power.
Huge amounts of energy. So if you mount your Starlink dish behind or even slightly below the plane of that spinning radar, you face two catastrophic issues. First, just the physical structure of the radar blocks the satellite signal.
Just a chunk of metal in the way.
Exactly. But second, and far more damaging, the RF energy from the radar pulse can completely overload the sensitive low-noise amplifiers inside the Starlink dish.
Wait, it can permanently damage it?
Oh, yeah. It's like shining a high-powered laser directly into night vision goggles. It just wipes out the receiver.
Wow. Okay, so you're navigating structural integrity, you're avoiding corrosive diesel soot, and dodging invisible planes of microwave energy. And the guide also points out the mechanical reality of the mount itself. It warns against attaching the dish to weak fiberglass without proper backing support.
Because of cyclic loading.
Right.
As the vessel repeatedly slams into waves, and we're talking thousands of times on a trip, the weight of the dish acts as a lever against the mounting surface.
Just pulling and pushing.
Constantly. And without heavy backing plates underneath to distribute that kinetic energy, the constant vibration will cause microfractures in the fiberglass.
Yeah.
And eventually the entire assembly will literally rip itself right out of the deck.
It's just incredible. Okay, so that covers the physical mount, but the electrical integration is where things get even more complex because a vessel's power grid is wildly different from a standard commercial building, right?
Night and day difference.
The guide stresses the need for clean, stable AC power from an inverter, properly protected circuits, and a rigorous grounding strategy.
Yeah, because a standard boat operates on a DC battery bank, usually 12-volt or 24-volt. But Starlink systems require alternating current, AC power, which means you must pass that DC power through an inverter.
And that inverter output has to be pristine. Because from what the guide says, a boat's DC system is incredibly volatile. Like if the captain drops the anchor and that heavy windlass motor engages, or the marine air conditioning chillers cycle on. It triggers these massive voltage sags and spikes across the entire electrical bus.
And those fluctuations will instantly fry a sensitive network power supply. Just gone.
Yeah.
The Starlink requires a pure sine wave to operate reliably, so the guide demands placing the power components in a dry, climate-controlled space entirely isolated from those heavy loads.
And you need aggressive surge protection in place.
Absolutely mandatory.
And the physical cable runs.
Yeah.
Like connecting that power supply to the dish outside, I really don't think most people realize how aggressive marine cabling has to be. I mean, in a house, you drill a hole, snake a wire, maybe hit it with some silicone, and you're done.
Right. Easy.
But on a boat, penetrating the hull or the superstructure is a critical structural event.
Oh, it requires marine-grade sealed penetrations. A poorly sealed cable gland doesn't just let in a little draft, you know? It allows pressurized saltwater intrusion during a storm.
And that water travels.
It travels right down the cable jacket, causing hidden rot and catastrophic electrical shorts deep inside the boat.
The guide also emphasizes heavy strain relief and avoiding sharp bends in the cable path. Which makes sense if you think about the physics. You have a heavy, shielded Ethernet cable hanging inside a vertical bulkhead.
Yeah, think about the G-forces.
Exactly. When the bow of the boat drops 10 feet into a trough, gravity and momentum just multiply the weight of that cable. So without mechanical strain relief holding it tightly in place, it will physically tear its own copper connectors apart just from the sheer force.
Exactly. Every single cable must be meticulously routed away from high-heat engine room spaces, completely protected from chafe against any sharp fiberglass edges, and perfectly secured.
Okay, so let's say you survive the installation gauntlet.
You did it!
You have dodged the radar energy, conditioned the power, sealed the penetrations, locked down the strain relief. You have 400 megabits of pristine data hitting the roof of the vessel.
Awesome.
But none of that matters if the owner sitting down in the lower deck master cabin is staring at a buffering screen. Right. So how does the signal actually penetrate the boat?
Well, this brings us to the internal network architecture, which honestly is arguably more complicated than the satellite link itself.
Really?
Yeah. The source material insists on the deployment of an entirely secondary enterprise-grade onboard network. The little router included in the Starlink box, it is entirely insufficient for a multi-deck vessel.
Because a yacht is effectively a floating Faraday cage.
Essentially, yes. I mean, you are trying to push a standard Wi-Fi signal through incredibly dense materials. Structural steel, thick aluminum, layers of carbon fiber.
And heavy, soundproofed solid wood bulkheads, right?
Exactly. These materials just absorb and reflect high-frequency radio waves. A single access point will never, ever reach the lower guest cabins or the engine room.
So the required setup involves dedicated marine network routers, heavy-duty Ethernet switches, and multiple strategically placed Wi-Fi access points just to blanket the interior.
Right.
And looking at the internal routing, the guide stresses stringent VLAN configuration.
Yeah.
Which makes perfect sense. You obviously need strict logical separation between the different users on board.
It is a massive security and bandwidth management requirement. Through virtual local area networks, or VLANs, you tag and isolate the traffic.
Because you don't want cross-contamination.
Right. You cannot allow a charter guest's, say, infected personal laptop to blindly pull the network and flood the vessel's critical navigation and engine monitoring subnets with broadcast traffic.
That would be a disaster. Or, a crew member's phone pulling down a massive background OS update that totally chokes out the bandwidth while the owner is trying to execute a remote stock trade.
Exactly. You use the VLANs to artificially throttle and prioritize those different traffic streams.
But the true genius of these marine network designs, and the element the guide really focuses heavily on, is the concept of redundancy and failover. Because Starlink is incredible, but it remains a single point of failure.
It is. If an unpredicted squall rolls in, or say you dock in a marina right next to a massive cruise ship that physically blocks your view of the sky,
The Starlink connection drops.
it will drop.
And for a vessel operating as a remote corporate headquarters, downtime is just unacceptable. The guide highlights systems like the MDS Blender or Peplink routers. Tell us how those actually function at like a packet level.
So these are advanced multi-WAN network management tools. Concord Marine uses them to aggregate multiple distinct internet sources simultaneously. So you aren't just running Starlink.
You got backups.
Better than backups. The system actually blends the Starlink feed with, say, a 5G cellular array for when you are near the coast, plus maybe a traditional VS connection for deep ocean backup and the local marina Wi-Fi when you are at the dock.
Okay, the guide uses the phrase speed bonding and true instant failover. And I really want to focus on the mechanics of that because it's not just a basic load balancer that awkwardly switches connections when one fails, right? It's session persistence.
Yes, and that is the critical distinction. In a standard setup, if your primary internet drops and the router switches to a cellular backup, your IP address changes.
Which means everything resets.
Right. Your Zoom call drops, your secure VPN tunnel collapses, and you have to sit there and reconnect. But speed bonding strips the data packets across multiple connections simultaneously.
So in practice, if you are presenting to your board of directors via video feed, and the yacht passes beneath a massive steel bridge that completely eclipses the Starlink satellite.
The connection stays alive.
Right. The Peplink system is already routing redundant packets over the 5G cellular network. So the video feed doesn't drop a single frame. The VPN stays completely locked. You clear the bridge, and the system seamlessly reincorporates the satellite data.
Exactly. The user never experiences even a microsecond of latency.
That is amazing.
It provides absolute enterprise-grade continuity. It basically operates as an invisible air traffic controller for your data. It's dynamically shifting loads based on real-time latency, signal degradation, and those user priority rules we talked about.
So we have established that to do this correctly requires structural engineering, RF hazard mitigation, pure sine power conditioning, VLAN traffic isolation, and tacket-level bonding across multiple distinct cellular and satellite arrays.
It's quite a list.
It is. Which brings us to the execution phase. Who is actually allowed to touch this equipment? I'll play the devil's advocate here. There's a huge DIY culture in boating. I mean, I've wired my own smart home, I build my own PCs. Why can't I just buy the performance kit, watch a few tutorials, and wire my own vessel?
Well, the guide draws a very hard line on this, separating casual, temporary setups on small day boats from permanent integration on serious cruising vessels.
Nope.
If you are just mounting a dish to a pole on a 25-foot center console, DIY is entirely appropriate. Have at it.
Once you cross into the territory of yachts with complex digital backbone,
You are introducing massive liability. The guide draws on extensive field data from Concord Marine's actual deployments out of Fort Lauderdale. And when you read through their operational histories, specifically looking at scenarios where they had to rescue botched amateur installations, you see the true stakes of the work.
Yeah, there is one highly specific case study mentioned involving a 68-foot Princess yacht. The vessel's captain, Captain Todd, detailed a scenario where a previous, totally unqualified company had botched a stereo installation.
Just a stereo!
Right. And the Concord technician, Rich Huglivina, had to come in and untangle what was described as a dirty disaster under the helm.
And see, a dirty disaster behind the helm of a 68-foot yacht isn't just an aesthetics issue with sloppy zip ties. The helm houses the vessel's digital backbone.
We're talking about the NMEA 2000 networks, right? The CAN bus systems that link the autopilot, the radar, the depth sounders, and the engine control modules.
Exactly. So when an amateur installer aggressively taps into power lines or runs unshielded consumer electronics cabling right next to sensitive data lines, they introduce ground loops and electromagnetic interference.
Which scrambles the data.
Yeah, they can cause massive data collisions on the CAN bus. So you could literally have a scenario where a poorly grounded audio amplifier or a botched router installation induces a voltage drop that causes the autopilot to lose heading data while the boat is running at speed.
Oh my God. So it physically degrades the safety systems of the vessel.
Yes, and that really underscores why integrating an enterprise Starlink system requires specialized technicians. They aren't just plugging in a router. They are ensuring the new hardware operates in total isolation from the vessel's critical nervous system.
They are verifying clean grounds, balancing the power load, and ensuring the entire integrated network from the Starlink array all the way to the 5G failover, is bulletproof.
Because the ultimate metric of success for this hardware isn't merely getting the system online. As the guide establishes, success is making the entire interconnected system completely invisible to the user.
It just has to work.
It must be brutally reliable, entirely automated, and structurally secure against one of the harshest physical environments on the planet.
Achieving that seamless, magical maritime connection is truly a masterpiece of invisible engineering. You need the ruggedized performance hardware to survive the elements. You must calculate precise structural mounting to avoid RF overload and cyclic fatigue.
Yep.
You need pure, conditioned power, meticulously sealed cabling, and a sophisticated multi-wand bonding router to guarantee the signal never stutters, no matter what happens to the sky above you.
It is a phenomenal synchronization of distinct engineering disciplines. It really is.
And it serves as a powerful reminder for all of you listening today. The next time you experience true technological convenience like pulling out a laptop and streaming flawless video while sitting on the deck of a boat miles offshore, remember the mountain of complex combative engineering happening right behind the bulkheads to make the illusion of simplicity possible.
You know, looking at this massive technological leap does leave us with a broader question to consider.
Oh.
Well, the engineering we've discussed today has effectively neutralized the isolation of the ocean. Historically, taking a vessel offshore was the ultimate method of disconnection. The sheer physical hostility of the sea meant you were unreachable. The ocean was a sanctuary from the demands of the modern world.
That's true. And now, with packet-level bonding and enterprise satellite arrays, we have basically transformed the middle of the ocean into an extension of the corporate boardroom.
Exactly. We have conquered the environment digitally. The network no longer drops. But we have to wonder now that marine technology ensures constant, inescapable connectivity anywhere on the water. How will that permanently alter humanity's fundamental relationship with the sea?
Yeah. What happens to the concept of getting away from it all when the office can literally follow you into the deepest water on Earth?
It's definitely something to think about.
That is a profound reality to grapple with. We spent decades trying to figure out how to force our most sensitive technology to survive the open ocean. And now that we've succeeded, we might realize we've lost the very isolation we used to seek out there.
Exactly. Something to keep in mind the next time you look out at the horizon. Thanks for joining us on this deep dive. And as always, keep asking what's happening beneath